to Math 480 again. You should turn in all of the homework that you graded from somebody else.
Start or not?
Yep. Turn in all the homework you graded from other people right here. So did anybody forget the homework that they graded? Okay. I also have all the graded homework from last time here. And I've just put it in this folder. The folder will go around. Also, if you didn't get your homework back from the time before, it's in the inner flap right here, okay? So I have all the homework that's ever been graded here. So just take it, leaf through it, find your assignment, and then take it out. Second, I looked over the feedback that you gave me very generously on Wednesday and just kind of summarized it. Of course, not everybody agrees with any of these statements, but most people did. First, a lot of people said that the course is not too hard, that there's occasionally a day that's hard, but generally speaking, the course isn't too hard, and that the pacing is fine. Some days it's a little too quick, some days it's a little too slow, so it sort of balances out to be about fine. There were a number of comments that people wanted to know a little bit more about underlying algorithms. So for example, if I say that Sage can do a certain calculation, you want to know more about how that calculation is implemented under the hood. What are the different ways of doing such calculations? Some people wanted homework problems that have more depth, so maybe a longer, more involved problem that involves using Sage in a less straightforward manner. So some of the problems I think have been more of a problem-solving style, but a lot of them have been fairly straightforward. If you knew Sage, it would be very easy to do many of the problems. So that was one comment. I didn't see that comment too much, but I did see it at least once or twice. A lot of people said they couldn't find any PDFs or worksheets for the lectures, and several different people said that. So since they have been posted every single day before class, maybe I should very, very explicitly tell you where they are. If you go to the Math 480 website, and click on Notes for each lecture, and then go to any random lecture, you will find a Sage worksheet and also a PDF for that day. The Sage worksheets are fine. The PDFs for some of the first few lectures have a little cutoff in some cases of the text. But that's been fixed on all the newer PDFs, and I will go back and fix that on the older ones. But it seemed like at least 5 people couldn't find the worksheets. I don't know why. But there they are. And in most cases, there's video as well. Somebody complained that Google Video is too low resolution, but there's little I can do about that. Except that much of the video is also at, well, for several days, the video is also, I'm posting the raw video as well in some cases. So if you do a little URL hacking, you can find it. So there is a bunch of raw video here. So these are the original MPEG files that come right off of the camera. And these are very high resolution. They're 640 by 480 resolution. And I have all the video, so I can just upload it. And if somebody really, really wants the video, it's all on the hard drive on the camera. So you can plug that into your laptop and copy it all off. Each file is about 1 gigabyte. So, and if you know a better way to post video than Google Video, let me know. Because again, the camera is really nice. It just records everything directly to MPEG files. It has a 60 gig hard drive in it. So it's not too hard to deal with. Let's see. There are a couple of people who wanted to know more about how to do Sage development, so things about coding conventions, how do you find the source code for things in the Sage source tree, what sort of environment do you set up if you want to start coding in Sage, etc. How is code ref read? And I will try to sneak some tidbits in like that as the course progresses. And there are definitely some people expressing worries about what the heck they could possibly do a project on, although I get the impression a lot of people are getting a reasonable sense of what they'll do a project on. By the way, I don't think people's projects necessarily have to take until the end of the quarter. I think it's possible somebody could propose a project, do some crazy weekend in a couple of days and just do it and then be done. So you shouldn't necessarily think that the project is something you have to turn in at the end of the quarter. It could be something you could finish more quickly if you just want to do a weekend of whatever, hard work. So I'm going to allow that to be something that you might consider. Okay. I thought this would be fun for a change. There's an open source software quote of the day from my inbox this morning. So here's a grad student at MIT named Tim Abbott, who he's one of the official Debian developers, and he is the project director of a project which has ported something called Athena to Debian. Athena being some huge collection of stuff for networking and all kinds of other things that MIT produces. And here's what he says. Wow. Thanks for making Sage such a great community to be part of. The Sage development mailing list is more friendly and positive than that of any other free software community I've participated in. The comparison is particularly jarring with Debian, which, as you may know, is famous for its flame wars. Debian is famous for its flame wars on their public mailing lists. Occasionally, they even get news coverage about flaming each other. I think it's really an issue of organizational structure. The project, referring to Debian, is very democratic and has a weak, annually elected leader, and they drove their founder away from the project. And so despite the fact that many Debian developers want to stop the flame wars, nobody has the authority to actually make people stop. There are definitely people who try. So maybe that little quote from this morning from somebody might give you some insight into the open source software that you might not have already. And how even big famous projects like Debian have a lot of trouble really maintaining a kind of positive community and staying well organized. And Debian is really huge. I mean, much, much, much bigger than the number of Sage developers. I have no idea how many Debian developers there are, but any estimates? I don't know. Probably well over 1,000 people. But actually, I have no clue. Okay, so the main topic today is linear algebra. So not matrix algebra like I did last time, but linear algebra. Just out of curiosity, how many people in here have taken a course in linear algebra where you learned about vector spaces and you learned the axioms of a vector space and verified that sets of functions form a vector space, that sort of thing? Okay, good. So pretty much everybody. Excellent. And a few hands that didn't go up just went up. So excellent. So just a brief reminder. A vector space is, well, defined it here. Recall that a field is a set with a multiplication and an addition, and one of the key distinguishing properties of a field is that every non-zero element has an inverse. A vector space is basically just an additive abelian group, but with a bonus. When you have, it's an additive abelian group and a field where you can multiply things in the field times things in the additive abelian group. And there are some consistency properties, like if you multiply an element of the field times the sum of two elements of the additive abelian group, that should be the same as multiplying and then adding. So that's the formal definition of a vector space is an abelian group and a field and a map from the field across the abelian group, which I'll call V, to the abelian group V, such that these compatibility conditions hold. Namely, what I just mentioned, basically things that look like the distributive and associative law, and some property that the one element is supposed to have. Okay, so that's a formal definition of an abelian group, or of a vector space. That's the abstract definition. And vector spaces are objects in Sage just like any other objects in Sage. Oh, by the way, here's an amusing picture of a bunch of vectors. So those are vectors. You can think of, so an example of a vector space that everyone's very familiar with is R3, and this is a vector space over the field R. A equals R, V equals R3, and this is a bunch of random elements. I guess you could think of them as vectors in the sense of physics, but here, when you say vector space, it's a little bit different because you literally mean elements of some additive abelian group. So here, they're just the vectors that go from the origin to some point. So in Sage, there are a couple of ways to create vector spaces. And there's a command, vector space, which is one way. You probably won't use this very much, as you'll see in a minute. But you can use it. And it takes as input a field and a dimension. And it gives you this particular sort of vector space. So one example of that generalizes this R to the n example is k to the n. Instead of all n tuples, that forms a vector space. So V equals k to the n for any n greater than or equal to 0. This is a vector space. So instead of all n tuples, it's an n-dimensional vector space. So e.g., for example, that's an example. And the command vector space in Sage allows you to create a vector space. In fact, this vector space. So for example, here, we say vector space QQ2. It creates a two-dimensional vector space over the rational numbers. I have to, I don't have my battery power, my adapter, so I have to do something. So here we go. Make a two-dimensional vector space. The data type is, it's actually, the data type is called free module underscore ambient underscore field that we get out. There's a category, in the sense of category theory, that vector spaces belong to. Just like elements, such as vectors, have some object they belong to, which is a bunch of vector spaces. Is a bunch of vectors belong to a single vector space, and then the collection of all vector spaces over a given field, that forms a category. Or even just all vector spaces over any field, that also forms a bigger category. How many people here know what a category is? Oh, not so many. So category is just another abstraction, like group, ring, or field. A category is a collection of mathematical objects and morphisms between them, where a morphism is like a linear transformation or something. It's sort of a generalization of that. The collection of all rings and ring homomorphisms, that forms a category. The collection of vector spaces forms a category. The collection of all groups with morphisms between groups forms a category. It's a very natural notion, and it comes up a lot in graduate level algebra. And then there's a notion of something kind of like a morphism between categories called a functor. So maybe I'll just draw a quick picture to illustrate this hierarchy. So you have elements such as vectors or matrices or whatever, and then these elements are contained in various parent structures such as rings, fields, vector spaces, groups, etc. And then these objects are contained in what are called categories. So categories up here. So here you have things like the collection of all rings, or the collection of all sets, which is not a set itself, or all vector spaces. So all vector spaces. So you have this sort of hierarchy. And it's something that you have in mathematics that any serious mathematician who's done much algebra will have in the back of their mind often when they're thinking about mathematics. But it's also something you have in Sage and in Magma. And also to some extent in MuPad and GAP, and in a couple of computer algebra systems. So you have elements, you have the structures that contain elements, then you have the bigger structures that contain the structures that contain elements. Okay? And there are whole books on category theory, which are basically about general theorems you can prove about categories of objects with and morphisms with given properties. Just like there are whole books on groups and on vector spaces and so on. Okay, so here's an example of making a vector inside of the vector space. This works just like making a polynomial in a polynomial ring, or a permutation in a permutation group. It all kind of works the same way. Vectors have type vector rational dense. Their parent is the vector space they belong to. You could do arithmetic, where you multiply a vector times a number on either side. And you can make vector spaces that are of huge dimension over whatever field you want, but any field here and any dimension here, and you get a vector space. So this is a vector space of dimension 10 million over a finite field of order 17. So is this object, this vector space, is it finite or infinite as a set? So I mean, first there's an object that I just made in Sage, which is just a Python class. In other words, that is basically just a completely formal chunk of memory that Python knows about in my laptop. But beyond that, the abstraction, this vector space, is it if you view it as just a set, look at its underlying collection of things, is it finite or infinite? Finite, right. Why is it finite?
You just have lots of permutations of...
or tuples. But
yeah.
You have lots of 10 million tuples. In fact, its cardinality is 17 raised to the power of 10 million. That vector space right there, which is GF 17 to the power 10 million, a finite set of order 17 raised to the power of 10 million.